Hey everyone, welcome back. It's been a while, but today we're going to be covering transformations, Math 30 concept that is pretty foundational for the units that will precede it. So, if we dive straight into this is what your basic fundamental transformation equation is going to look like. It's going to follow these set of variables, basically. You have these different parameters which are going to differently affect the way that your graph is going to look. So we begin. I'd like to start off with our A value. So our A value is going to be a vertical stretch. And this is going to be by a factor of A. So what does this mean? Right now you don't really have to worry about that, but when you're going to be asked to describe these transformations, all of these transformations are going to follow a pattern. So when you're describing the A value, it's a vertical stretch by whatever A is equal to. So yeah. And this is going to be about the x-axis. And the way I like to kind of envision this is if we were to draw out a graph, and let's say it looks like this. If we were to stretch to look something like this, you can see that it is being kind of compressed or either stretched from this x-axis here. So in this case, whatever this would be a vertical stretch. So you can just imagine like you vertically pulling the graph in or out. And that's how I like to imagine this. But if you were to actually test this parameter of A, we'd write it on the outside of our equation. So what does that mean? So you have a couple of ways you can express a vertical stretch. You could say that a vertical stretch is like 3y is equal to x squared. And then from there, you would divide by 3. So you get 1 over 3 x squared. And this would be your vertical stretch by a factor of 1 over 3 about the x-axis. So now if you were to compare the graph of x cubed, so if we want to pull out our calculator here. So we can compare these two graphs here, where the blue line is going to be y equals x cubed. And then you have our red line, which represents y equals x, 1/3 x squared. So it's stretched by a factor of 1 over 3, meaning that every y value is going to be multiplied by 1/3. So again, we're going to have some points that are going to stay the same here. As you see, like our x-intercept of y is equal to 0, and if you multiply 0 by 1 over 3, that's not going to change anything. But you do notice that this graph starts to get somewhat wider, it looks like. So the reason why our graph of 1/3 x cubed is going to look wider is because the y values are going to rise more slowly, and it's going to take longer to actually get to the same point. So yeah, I mean, it's easier to envision with a linear function, so I guess we'll try it with a linear function. So if we had y is equal to, let's say 1/4 y is equal to 2x, or say x plus 3, and then you multiply by 4, you're going to get 4 times x plus 3 is equal to y when you multiply by both sides. In this case, you would have a vertical stretch by a factor of 4. So if you want to graph the graph of x plus 3, that would start at 1, 2, 3. This is not going to be the scale, but it's going to look something roughly like this. And if you were to graph the graph of 4 times x plus 3, we go in our graph here, not like you need it, but just in case. 4x plus 3. So your graph of y equals x plus 3 is going to look something like this. And you're going to find that when you graph y equals 4x plus 3, that's going to be a lot wider. So this is a vertical stretch. You can either make it wider, you can make it smaller. And again, it's going to be about the x-axis. So now, what happens when a is negative? And how do we describe this? So when a is negative, there's going to be a reflection in the x-axis, or the line y equals 0. That's another way to write it. In the x-axis, or the line y equals 0. So now if we were to compare the line of x plus 3 to the line of negative y equals x plus 3, you get negative x plus 3. And you'd see that a is equal to negative 1. If you want to compare these two, you'd see that there is going to be a reflection in the line y equals 0. So if we were to graph these two graphs here, you'd see that if we were to type in y equals 0, this is going to be our line of reflection. So in terms of invariant points, invariant points occur on your line of reflection. So where both graphs intersect the line of reflection. So in this case, where y equals 0 for both graphs. That is all the invariant points are going to be. And the way you describe a reflection is you just say, instead of a stretch, you have to separate the stretch and the reflection. So I'd say there is a stretch or a reflection in the x-axis. Reflection in the x-axis. Now, when you have both a stretch and a reflection, for example, let's say you had an equation that looks like this, or a graph that looks like this, you describe this by stating your stretch first. So I'd say there is a vertical stretch by a factor of 1/3 about the x-axis, and a reflection in the x-axis. And that's all you gotta know for this parameter a. Just know you're stretching, and it's going to be about the x-axis. And you're stretching by a factor of a. Now, if we take a deeper delve into the parameter b, it's going to be a similar scenario. We're going to have b is going to be a horizontal stretch. So it's a horizontal by a factor of 1/b about the y-axis. Now, effectively, this is going to be the opposite of our vertical stretch, because we're going to have a vertical or horizontal stretch by a factor of 1/b. It's always going to be 1 over whatever your b value is in your equation. So for instance, if we had this equation here, y equals 2x minus 3, and we factor out this 2, because remember, we're always trying to factor out whatever's in front of x to get this b value isolated. So I'd get 2x minus 3/2 after factoring that out. It's going to be equal to y. And you'd say this b value is now equal to 2, right? So the way you would describe this transformation is you'd say there is a horizontal stretch by a factor of 1/b. So 1/b is going to be 1/2, since b is equal to 2. Of 1/2 about the y-axis. And again, you can test this parameter out. The only difference between the horizontal stretch is it's going to be inside the brackets where x is, and it's going to affect the h parameter, whereas the a value is going to be outside of these brackets. So make sure you're able to differentiate between the two. But in terms of this, if we were to compare the graph of graph of y equals 2x minus 3 compared to just x minus 3, because then this would just be a horizontal stretch by a factor of 1/2. So let's compare these two graphs here. So you have the graph of 2x plus 3. And you're going to compare this to x plus 3. So we now see that the graph of 2x plus 3 is a lot more steep than this graph of x plus 3. A general rule for the stretch values is when it's a whole number, it's going to get more steep, and when it's a fraction, it's going to get more wide. I don't think you're going to have to worry about that too much. Just know what each parameter does. Like if you were to compare this, if we had a vertical stretch by a factor of 2, which would be written in our equation as 1 over 2, because we have to have 1 over b, remember? This would be a vertical stretch of 2. And we compare these two parameters. So it's a 1 over 2 x plus 3. You can just compare these three lines. So you see this last and final graph here, it's a lot more wide when it's a fraction, opposed to a whole number. Now, when b is negative, what happens? You're going to have another type of reflection. This is going to be a reflection in the y-axis. So remember that a affected the x-axis. This one reflects the y-axis. So it corresponds with the same axis. So it's going to be consistent between the two. So a horizontal stretch about the y-axis, a reflection about the y-axis when b is negative. A is going to be a vertical stretch about the x-axis and a reflection in the x-axis. So it's going to be consistent between the two. Now, what does it mean to reflect in the y-axis? So if we were to draw this out, this is our x, this is our y, and effectively our y line becomes a reflection line. So if we had a graph that looked like this, and this would probably be the graph of y equals x, to reflect in y means to reflect along this line. So you're going to get something that looks like this by reflecting in the y-axis. And all this transformation is just a negative b value. So you're going from x to negative x. So for instance, if we had y equals x, our reflection in the y-axis would look like y equals negative x. If you want more examples, a reflection in the x-axis of x plus 3 would turn into a negative x plus 3. So when we have a negative x attached to this bracket, in this bracket that affects the parameter h, we're going to have something that's dealing with the value b, the parameter b. So if b is negative, then we have a reflection. So the way I describe this is there is a reflection in the y-axis. Now, if you want to compare these two graphs, again on the calculator, because this is a very hands-on kind of calculator unit, I'd say we have graph of y equals x compared to negative x. And then you can see that it's going to be reflected in this line. And notice how the invariant points are going to be on the line of reflection, where both graphs intersect the line of reflection. So you're always going to have your invariant points equal to the line of reflection. And invariant points are just points that stay the same between both graphs. All you have to do is just know that when b is negative, you have a reflection. And the way you describe it is going to be the same. You state your stretch and then your reflection. And that is what the parameter b represents. So now, when we take a look at the parameter h, what does this actually stand for? Notice how we're subtracting from x here, meaning our h value right now, as of right now in this equation, is going to be positive. So h is positive when we're subtracting from x. And if we were to add to x, like if we were to have a negative h value, it would be then x plus h, whatever h is. So just keep that in mind. It's very important. It's a very important concept that when h is negative, you're going to be adding to x. And when h is positive, you're going to be subtracting from x. So what does this h parameter actually stand for? H is a horizontal translation. So we've had stretches, and stretches are where you multiply. Translation is where you directly are going to shift your graph either up or to the left or right. Up, down, left, right. But since we're dealing with x here, we're going to be dealing with the x plane. So if you think about this, we're going to be translating either right or left. So if h is positive and we are subtracting from x, then we are going to be moving right. So we're going to be translating h units right. Now, if h was negative, and we are adding to x. So x plus h, we're going to be moving h units left. So we're going to be moving h units left. And the way we describe this is you would have a horizontal translation. H units, either right or left, dependent on if h is positive or negative. Now, if you're unsure what this actually means, I can pull up a few examples here. So one of the examples I like to use is the graph of a quadratic, right? So graph of x squared has currently no stretches, translations, any transformations applied to it. So this can be our reference graph. So our graph of y equals x squared is going to look something like this. Now, if we were to add a horizontal translation, x minus h, let's say we want x minus 3. So we would plug in x minus 3 squared. Based off what we said earlier, we're going to have a horizontal translation since h, we have an h value here, and our horizontal translation is going to be to the right, right? Because we have x minus h, and h in this equation is greater than 0. So our h is greater than 0, and our h is equal to 3 in this case, positive 3, meaning we're going to be moving h units right. So h units right, we have a horizontal translation, h units, so 3 units, right? So every graph of the graph, or every point on the graph y equals x squared is going to be moved 3 units to the right. So instead of our vertex being at 0, 0, it's now going to be at 0, 3, so somewhere over here. And every point is going to be moved 3 units to the right. So we're effectively just shifting this whole entire graph 3 units right. The purple would be y equals x minus 3 squared. So now I want to deal with the inverse. So what if we were to add 3? We would notice, since we're adding to x, our h is going to be negative. So our h is negative, and we are going to be moving to the left. So h is negative. We're going to be moving to the left. So h units left. So we have a horizontal translation, 3 units left, since we are again adding to x. Now, what we can do is we can draw this out. Our original graph of y equals x squared was at 0, 0. And now if we move it 3 units to the left, it should be somewhere over here. All I want you to take away from this is that when h is positive, you're going to be moving right. When h is negative, you're going to be moving left. And when h is negative, you're going to be adding to x, so x plus h. And when h is positive, you're going to be subtracting from h. And that is the parameter h, which determines horizontal translations. Now k can be represented in a funny way, actually. The k is different in that if it is negative, you're moving down. So it'll directly be proportional to whatever it is. So whatever sign it is. So I'd say that if k is positive, you're going to be moving up. So this one's a lot more simple. If you had the graph of y equals x squared plus 3, and notice how the h value is not present because we have x in brackets, and this k value is going to be outside of that. So y equals x squared plus 3. We'd have a vertical translation. And this would be 3 units, either up or down. So I'd say this is a vertical translation. Three units up. It's going to be up because k is going to be positive. Now, if we had the graph of y equals x squared minus 3, it's going to be 3 units down because k is negative. This one's pretty simple. And if you want me to graph it out, I will be doing that. So let's say our original graph is the graph of y equals x squared. And now, if we were to translate this graph of y equals x squared 3 units up by adding 3, you'd see it'd be higher 3 units up. So here, the graph of y equals x squared is going to be the red graph, and the blue graph is going to be the first equation we wrote down. And notice how the vertex is 3 units higher, and every point on that graph is 3 units higher than the original. Now, if you were to subtract 3, it's going to be 3 units lower than the original graph of y equals x squared. So that is just what I want you to be cognizant of, and just realize that these variables or these parameters, and be aware of how these different parameters affect how the graph is going to be translated and how to describe it respectively. Now, in terms of the order of describing all these transformations, you're going to want to describe it in the order of stretches, then reflections, then translations, just following in order of operations. So as long as you guys do that, I will be posting a video about mapping notation and doing some diploma questions, and kind of further going over this concept, as this is just a very broad video, just to introduce you to transformations. But if you guys are looking forward to that, just let me know. Thank you guys so much for watching this video. I put a lot of effort into these, so yeah, I hope you guys enjoy. Thank you so much, and that'll be it for me.